All right, for our grand finale, we are going deep. I mean, all the way down to the atomic level. We're about to uncover one of the wildest connections in all of tech, how just, drawing a circuit has become an act of engineering physics itself.
So let's kick things off with a question that sounds super simple on the surface, but is really a massive mystery at the heart of modern chip design. How is it that on a chip with billions of transistors, you can have two that look completely identical but act totally different? Like, what is going on there?
Well, the answer starts with an absolutely huge investigation. Researchers built a special 7-nanometer test chip, and they didn't just measure a handful of transistors. No, they measured over 30,000 of them. And each one was intentionally placed in a slightly different neighborhood. You see, they were hunting for something called local layout effects, or LLEs for short. And the whole idea here is pretty profound, actually. It turns out a transistor's performance isn't just about what's inside it. It's hugely influenced by what's around it. How close is the next wire? Where are the connectors? It's like its neighborhood is literally changing its personality.
And after digging through just mountains of data, they found the culprit. And you know what? It wasn't what you might expect, like electrical noise. Nope, it was something invisible, mechanical stress. We're talking about tiny, tiny forces from the manufacturing process that are literally squeezing and stretching the silicon atoms, completely changing how electrons can flow.
Okay, now this is where things get really wild. Check out how different kinds of transistors react to the stress. Over on the left, you've got the PMOS devices. They have this really clean, predictable response. As the stress goes up, their performance changes in a nice, neat line. But then you look at the NMOS devices on the right, and whoa, it's a totally different story. Their performance is all over the map, because they're getting pushed and pulled by all these different forces at the same time.
And all of this reveals what you could call a golden rule of stress in chip design. It's kind of crazy when you think about it. The exact same force, a compressive squeeze, does opposite things. It actually boosts the performance of PMOS transistors, making it easier for their positive charges to zip through. But that same squeeze degrades the performance of NMOS transistors, which carry negative electrons. So one gets a boost, the other takes a hit.
So how on earth do you even see these invisible forces? Well, engineers use this incredibly powerful software called TCAD. That's Technology Computer Aided Design. And the best way to think about it is like a virtual CT scan for a single transistor. It lets them build this full 3D model and literally visualize that hidden, complex world of stress inside the chip.
Okay, so there's a huge catch here. TCAD is amazing for seeing the physics, right? But a single simulation can take hours, sometimes days. You obviously can't design a chip with billions of transistors like that. It's just way, way too slow. So the big question is, how do you take all this deep physics knowledge and actually make it useful for millions of circuit designers?
The answer? You build a bridge, a way to translate all that complex physics into the fast, practical language that circuit simulators like SPICE actually speak. And this table is brilliant. It shows you exactly how that bridge gets built. The engineers literally map the physical effects they see in those slow TCAD simulations directly onto specific parameters in the fast models. So for instance, when stress changes the drive current, that gets translated into a number for the U0 mobility parameter. Or if the turn-on voltage shifts, bam, that becomes the DVT P0 parameter. All that deep physics gets boiled down into a practical set of numbers.
And this whole translation gets encoded into something called a compact model, specifically BSIM-CMG. It's really a masterpiece of abstraction. It's just a lightweight set of equations that captures the essential physics without needing a supercomputer to run it. It's basically the universal language that every single chip designer speaks.
Okay, so we've got our model. Now let's see how this all gets turned into a rulebook that designers can actually use to build, well, everything. All of that intelligence, the measurements, the physics simulations, the BIM models, the whole shebang, it all gets packaged up into what's called a Process Design Kit, or PDK. You can think of this as the official rulebook that the chip factory, the foundry, gives to the designers. It has literally everything they need to know to make sure their chip will actually work on that foundry's specific process. So let's put it all together. Here's the entire journey, right? You start by characterizing thousands of real devices. Then you use TCAD, those virtual CT scans, to model the deep physics. You translate that physics into a fast, usable model. And finally, you embed all that knowledge into the PDK, that super important rulebook. And this whole feedback loop, that's what we call Design Technology Co-Optimization, or DTCO.
But
there's a problem. This amazing process is starting to hit a massive wall. See, as chips get more and more complex, the number of possible ways you can lay them out just explodes into the millions, billions. Running those slow TCAD simulations to check everything is becoming impossible. We're back to that same bottleneck: speed and scale.
And this right here is where the next huge revolution in chip design is kicking off. To smash through that bottleneck, the industry is turning to AI.
So here's the game-changing idea. Instead of running a super slow, physically perfect TCAD simulation every single time you have a new layout idea, what if you could use that data to train an AI? You create what's called a surrogate model, basically an AI that learns the physics so well it can give you an instant prediction.
Using machine learning techniques like Gaussian process regression, an AI model can learn that incredibly complicated relationship between the layout geometry and the physical stress it creates. I love this analogy. It's like an expert who studied thousands of these simulations and now just has an intuition, an ability to instantly guess the right answer. So once it's trained, it can predict a new layout's performance in milliseconds. Not hours, not days, milliseconds. This just unlocks a whole new universe of design possibilities.
But of course, the challenge just keeps getting harder. As we look to the future, we have to deal with the fact that real layouts don't have just one simple stress effect. No, they have tons of different effects all overlapping and interacting with each other, creating these compound LLEs that are super unpredictable.
In this image, wow, this really shows you how relentless this industry is. We're already moving beyond the FinFETs we've been talking about. The next big thing is even crazier 3D structures like these gate-all-around or GAA nanosheets. The name says it all. The gate literally wraps all the way around the channel.
Now these new GAA devices are amazing. They give designers way better electrical control, which is great for performance and power. But here's the thing, they absolutely do not solve the fundamental physics problem of mechanical stress. In fact, you could argue their super complex stacked structures make predicting that stress even harder.
And this really brings us to the single most important idea of this whole series. It's this. In these advanced nodes, the layout isn't just a drawing anymore. It's not just geometry. The act of drawing those lines on the screen is a direct manipulation of the device's physics, right down to the atoms.
That line between being a circuit designer and being a physicist, it's gone. It's completely blurred. And as we start to hand more and more of this incredibly complex task over to AI, it leaves us with one final fascinating question to chew on. What does it even mean to design something when your designer is an algorithm navigating a world where the drawing and the physics are one and the same?